to the matrices, we have this rank nullity theorem. So we have seen before this theorem, the rank nullity theorem for matrices, but this works the same way also for the linear transformations. So for any linear transformation T from V to W, we have that the rank of T, so the corresponding rank of this linear transformation plus the nullity of T, this is equal to the dimension of V, okay? So in principle, we should also, as a reminder, so if we are kind of confused here, we can always look at this 3 by 5 times a vector V, which is 5 by 1. So it looks like this dimension of V will be in fact the number of columns of A, where the number of columns, where A is the matrix representation of the respective linear transformation. Okay. Now we move to the next important topic, which is the coordinate change. Okay. So this is the most important part of linear algebra. And when we talk about the coordinate change, I'll try to make the big picture that we're going to talk here. So we are going to have the general idea is the following. We have a basis which is considered the standard basis. So standard basis, okay? We talked about the standard basis in the first session, so I believe it is clear. And now, next to this standard basis, we can have another basis which we can call this one basis B1. Okay, so this is the basis B1, and the numbers that define this basis could be the following: 1, 2, minus 1, 2, minus 1, 4, and 3, 2, 1, 3, 2, 1. Now, this could be a basis, and a basis would be the columns serve as basis. So just so that we are a bit clear, the column can constitute a basis. But then we can always ask the question, we can suspect, we say, is it really a basis? So if you are in an exam, and you have to figure out whether this one is really a basis or not, what are you going to do?
Check the determinant.
That's true. So we check the determinant. If the determinant is different from 0, then we say that this is really a basis. Now here, we can have another basis B2, okay? And this basis B2, we can have other vectors as a basis, which would be 1, minus 1, 0, 2, 0, 1, 3, minus 2, 1, okay? So we can check again the determinant of this new matrix. And if it is different from 0, we say that this is also one possible basis. We know what is the standard basis. What is the standard basis? It's represented by 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, what we can do is that for any given vector in B1, if we are given a vector in this domain, okay, if we write a vector down here, that means that we are going to report the projections or the coordinates in this basis, okay? If we give a vector here, so let's give a vector here which would be 3, minus 2, 1. What does this vector mean in standard basis? This means that the projection along the x-axis, it is 3, which means that the projection along this 1, 0, 0, it is 3. The projection of this vector onto the second axis is minus 2, but where? 0, 1, 0. The projection along the third axis, it is on this one, it is equal to 1. So this is what we mean with these vectors. Now, assume that we have a vector which is 4, 1, minus 5. 4, 1, minus 5. But this is in basis B1. So what does this mean? We say the following. We say that this vector, according to the basis B1, this is, we multiply the projection along the first column, it is 4. Okay? The projection along the second column, it is 1. and the projection along the third column, it is -5, okay? And how do we denote this? This coordinate here, we denote it as follows. We say that this vector x, according to basis b1, it is equal to 4, 1, -5, okay? And then the question is, the following important question is the following. How, I forgot, this is wrong, we should not forget that this is according to the basis b1. If we put no b1, b2, or any other basis notation, that would be in standard notation, in standard basis. So now, the question is, how does this vector look here? So how this vector project onto this basis? How can we find that? What we can do for that is the following. Now, we are in this basis, and if we want to see how they look like in the standard one, we should do the following. We do 4 times 1, plus 1 times this, -5 times this. Do you find this intuitive? What do you think? -5 times 3, 2, 1. So let's see what we get here. 4 plus 2, 6, minus 15, minus 9. 8 minus 1, 7. 7 minus, what is this? 8? No, 8 minus 1, 7. 7 minus 10, minus 3. Minus 4 plus 4, 0, minus 5. Okay, here we are. So what is this vector in the standard basis? It's -9, -3, -5. -9, -3, -5. Okay? So this vector in the standard basis, this is how it is going to look like, okay? And but how did we do this? Çfarë bëm në orën e parë? Tani duhet të mendeni të gjithë. Orën e parë çfarë thamë? Ne thamë që këto vektorët, nëse këto janë projeksionet të këto 3 boshtet, të këto 3 kolona. Si e shkruhet më? Besoj se këtë pjesën e pranojmë. Ja po kap njëri këtu në klasa. Këtë kap Dora Driloni. Driloni. Driloni, can you follow me? Okay. So, Drilon, do you find this intuitive or reasonable? Drilon? So we were given the projection of this vector onto this basis B1, and it looks like the projection on the first column, on the first basis vector is 4, and the second one is 1, and the third one is -5. Would you agree with this notation, Drilon? I think yes. Okay. If you go back to the class notes from the first hour, you are going to see that this is true, because any kind of representation like this means that 4 times the first column. This means that we can put here 1, 2, -1. Okay, and we know that if we multiply each row, imagine for a moment we're multiplying the first row with this column. The 4. Kjo kadra gjithmonë shumëzon 1, 2 minus 1, dakor? Pra kjo është 1, kjo është -5. Pra kur bëjmë shumëzime që do na dalë një rezultat këtu, kjo kadra gjithmonë kjo shumëzon. Kjo 1 do shumëzohet gjithmonë te kolona e dytë, që do na vitë 2 minus 1 4. Besoj se kjo pjesë është e qartë. Edhe kjo -5, this -5, it is always going to pick up the numbers that are the third, because this is how we do the multiplication. We do this row, we multiply with this column, and it looks like the 4 will be always projected onto these, right? Në gjithmonë dhe -1 4 plus 4 1 plus 1 -5. Je dakord, Driloni? No. Why? Okay, so then this means that if this is the basis, we can write this calculation to find the projection of a vector in the standard basis. So this is -9, -3, -5, and this is equal. So what did we do here? What we did here is that we had a matrix P1 times the projections of the vector on the basis B1, and we found the vector x in the standard basis. If we write it like this, we understand that this is the standard basis. We don't care where it's coming from, okay? So now, so this is what we should remember. This means that to any vector here, we can apply the matrix P1. So we can go from the B1 to standard basis using matrix P1. Similarly, if we are in basis B2, we move this way using a matrix P2. Where is this matrix P2? It's right here. Kjo baza që pretendon që është bazë për të hapësirën, the allegedly correct basis can construct a matrix P2, and they all come to the standard basis. Now, we did this calculation here. Now I want to use the board again. Maybe I can write it like this. So imagine we can write another basis B3, okay? And the B3 is going to have another basis, and here we come down using a matrix P3. This is what happens. Always the basis of each domain constructs a matrix, and all of these matrices, which would be this, or whatever P3 looks like, të gjitha të dërgojnë të baza standarde. Okay? So I want you to remember this. And before starting the coordinate change, we are actually already doing the coordinate change, and we see that the coordinate change is done using the basis itself. Okay? And this is how we move around. Now, another question. Oh, okay, I can also ask you this. If we are given 9 minus 3 minus 5, how can we find how does this vector in standard basis look in basis B1? Simultaneously. If we are given this, how can we find the projection of this onto the other basis?
Duke pjestu me standard basis, ndoshta?
Duke pjestu?
Basis.
Are using the inverse of P1? Okay.
That is correct, okay? So what do? We say P1 times x according to basis B1. This is going to be equal to x. What we can do here, we can multiply from both sides with P inverse. Maybe it's better if I erase this. So if we have this, and this equation is already written here actually, so it's not, then this is equal to x. We can multiply from both sides with P1 inverse, and here we have P1 inverse. So this P1 inverse with P1, this is equal to identity matrix, so we get that the projection of any vector x according to basis P1 is going to be equal to P1 inverse times x, which means that we can come backwards using P1 inverse, okay? And similarly, we can also go from the standard basis to basis B2 using P2 inverse. And similarly, we can go here with P3 inverse, okay? So if we are given minus 9, minus 3, minus 5, we don't divide by the basis, but we multiply with the P1 inverse, and we should get this. So if we are given this vector, 3 minus 2, 1, what is going to be this vector in the basis B1? We need to find the P inverse, and then we multiply we do the following. We say P1 inverse times the given vector, which is 3 minus 2, 1. We're going to find some values, but we don't know yet the P inverse, but I believe that what is here on the board is enough to explain the essence of what the basis changes does. Do you have any question for what is on the board? Any question? Now, I never explained this topic this way. So normally we provide the formal definition by providing the theorem, the definitions, etc. And then we move into the examples. But now that you have a little bit of the feeling of what is on the board, and now that you understood this, it will be easier for you to understand the formal definitions, which are sometimes tricky to understand. So what we say here is that assuming that if Vi is a basis B in Rn, okay? So Vi is a basis B in Rn. In this case, what is the basis? V1, V2, V3. These are the columns. This is the basis B1 in R3. Okay, so let's not forget whatever is here is on the board. Everything all around, they are all here. Okay, that's what they are, because each column vector is composed by a triplet of numbers. So here we have, if Vi is the basis of B in Rn, that means that X vector is in Rn2. Okay, that's for sure. And then this X, any vector X, can be written as alpha I times Bi. Okay, so in this case, and what is alpha I? Alpha itself, it's a vector which is composed of alpha 1, alpha 2, up to alpha n, assuming that there are a lot of these alphas. In this case, what is V1, V2, V3? These alphas are constant numbers, which are in this case 4, 1, minus 5. Okay? But it doesn't have to be up to 3, it can be many values of alpha I, depending on the dimension of the Rn. So then, if this is the case, then we can denote that X, according to basis B, is equal to alpha 1, alpha 2, alpha n in according to the basis B. And then we can say that the vector X in the standard basis, so let me write it here, standard basis, SB, okay? This is going to be equal to a matrix which is holding these columns V1, V2, Vn, okay? So these are all columns, okay? They are put as times alpha 1, alpha 2, and alpha n. But this should be according to the basis B. So these are the coordinates. And let's not forget, we are talking, the topic of discussion right now is this. So we are doing coordinate change, so we want to change these numbers, which are the projections onto different bases. Okay, so I believe this is all that we need for the okay. We just have a druga draza.
Dugat makeć.
Okay. Tot tani kom je super.
Ja.
Prap duket që si edhe.
Okay, så I kan drida. I kan drida, të thonë përsa kotatër, se kompjuteri më punon. E kam lidhë në celularin. Edhe internetin e kemi nga me kështu, si quhet, çfarë quhet teknika që you share your hotspot internet, but okay, so now probably you might find this a little easier to understand all the formal definitions of the coordinate change or the basic principles of coordinates now that we went over this example. But it is worth doing an example that can help us understand a little better. Now, is the board, a shikoni të rasë pak më mirë?
Po.
Okay.
Po.
Në fundit. Maybe this is enough. Okay, let's see an example. So, given a basis B, so given basis B1, and let's assume that our basis is this one that we have provided here, and we are given the coordinates of 4, 1, minus 5. So, okay, so given these coordinates, in B1 as 4, 1, minus 5, the question is, wait a second. Yeah, the first question is find x. So this is the first question. Now, how can we find x? We already did it. We said that if we are given the bases, which are here, we multiply all of them individually by the coordinates, and the x in this case would be this minus 9, minus 3, minus 5, which is given here. Now, another question that we can add here is try to determine given x equal to 3 minus 2, 1, 3 minus 2, 1, find this x in basis B1. Okay, so how can we do it? We said that we have to find the P inverse, and we have to multiply with the projection of the vector in the standard basis. Now, P inverse is equal to, so we can write it here, this is going to be equal to 1 over 4 minus 9 minus 4, 7, minus 9 minus 4, 7, 10, 4 minus 6, 7, 4 minus 5 times 3 minus 2, 1. Okay? So the projection then is going to be equal to these numbers, and these numbers, they are equal to, let's have here 1 over 4. So 1 over 4, here we have minus 27, minus 20, minus 47, minus 47 plus 7, minus 40. Then we have 4 times 3, 12, 12, no, minus 12, minus 8, minus 20, minus 20 plus 4, minus 16, minus 16. And then we have 7 times 3, we get 21, 21 plus 12, 33, 33 minus 5, we get 38. I believe that is correct. I could be wrong, but let's do this again. 21 minus 12, no, oh, that's plus 12, 33, 33 minus 5, 28. Okay, sorry, this is 28. This is 28. So if we divide them by 4, then what we get is minus 10 minus 4. And then we get 7. So these two vectors, because we have many vectors here, I just want to note that those two are equivalent, but we should know, we should make no mistake when we determine this. So this one is going to be equal to P inverse times this. So we apply this vector P1 inverse onto this vector. Now, what we can similarly try to do is the following. So we can give another, because playing with numbers, it might take a lot of effort to find all the inverse matrices. They are computationally complex. They are computationally expensive. Not to do it in a computer, but at least to do at least on the board. It might take some time for us. But let's assume another vector, which is here 1, minus 2, 3. So this vector in basis B2, what is it in the standard basis? We don't need these. So the question is, given x in basis B2 equal to 1 minus 2, 3, find x in standard basis. How would we find that? Any comment?
1 times the first column in basis B2.
Yes, 1 minus 0. Yes.
Times the second column in basis B2. And 3 times.
That is 3 minus 2, 1. It's 3 minus 2, 1. And this is going to be equal to 1 minus 4 minus 3 plus 9, 6. Minus 1 minus 6 minus 7. And then we have minus 2 plus 3, 1, 6. So then, in the standard basis, this is 6 minus 7, 1. So these two vectors, they are linked together, and we know that we go from one to the other using P2. And this is, so let's call this one, for the sake of the notation, that is big P2. Now, we may try to determine what is P2 inverse, but as we said, it might take some time. Well, it would even be a little easier. So if we add these two together, we get 0, 2. Let's try if we can find it. 1, 2, 3. 1, 2, 3. Minus 1, 0, minus 2. 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So if we add them together, we get 1, 2, 3. This is 0, 2, 1. If we add these two together, we get 1, 1, 0. And then we can 0, 1, 1, 0, 0, 1. We can divide this by 2. This becomes 1. 0.5. 0.5 and 0.5. Then we can do this minus this. If we can subtract 1 minus 1, this is 0. 1 minus 0.5, it is 0.5. 0 minus 0.5 minus 0.5 minus 0.5, this is 1. Then the next step is multiply by 2 everywhere. Why did this happen? Wait a second. You want to get it? Okay, so we can multiply here by 2, and what we get is that this is 1 minus 1 minus 1. 1 minus 1 minus 1, 2. And then we should subtract, but we should also, oh, no, we are doing all the steps. So we can subtract here 0.5 minus 1. This is minus 0.5. 0.5, no, we should do it differently, that's wrong. We should subtract half, not the whole thing. 0.5 minus half of this one, we should get 0. Minus half. So this is 0.5 minus 1 over 2 times minus 1. What is this equal? This is equal to, what is
1.
This? Is it 1? Here it is 1, right? It's 1. Because it's easy to get confused. I think this is also 1. 0.5 minus 1 over 2 times minus 1 plus 1 over 2. This is also 1. This is also 1. This is minus 1 then, right? This is minus 1. Then we have to subtract 3 times the third row. So this is 3 minus 3, 0. 3 minus 3, 0. Then this is 1 minus 3, this is 4. Then this gets 0 minus 3, this gets 3, 0, minus 6, minus 6, and then this looked like relatively easier. So then, but you can double check this one on your notebooks, okay? We might have done some mistakes. We subtract twice from here, 2 minus 2, this is 0. Then 4 minus 2, we should get here 2. 3 minus 2, this is 1. 6 plus minus 6 plus 2 minus 4. Minus 4, okay, so it looked like we did it. So it looks like we did it. This is P2 inverse. So we found P2 inverse, which means that if we want to find so where did we start? We start from 4, 1 minus 5. We found 9 minus 3 minus 5, and we would be interested to look at what does this vector in basis B1, how does it look in basis B2? How can we do that? We can say that this P2 inverse, which is, assuming that we made no mistakes, okay? If we made some small mistakes, you can correct this one at home. Minus 1, 2, times the vector minus 9, minus 3, minus 5. Minus 9, minus 3, minus 5. And this is going to be equal minus 18, minus 3, minus 21, plus 20. It's minus 1. Then we have minus 9, minus 3, minus 12, plus 5, minus 7. Minus 7, then we have 9, plus 3, 12, minus 10, it's 2. So this is minus 1, minus 7, 2. Minus 1, minus 7, 2. So it looks like, let's try to draw this one to look at. We should not interfere too much, but this is the same as in here. Okay. So it looks like we could easily, when we say easily, for some it could be painfully, calculating inverse matrices very fast, but it looks like as a result, we notice that if we have the original vector 4, 1 minus 5, 4, 1 minus 5, what did we initially do? Initially, we multiplied this 4, 1 minus 5, which was according to basis B1, we multiplied with the matrix P1. Then we multiplied with matrix P2 inverse, and we got what? We got minus 1, minus 7, 2. This was equal to minus 1, minus 7, 2. But this is according to basis B2. Okay, so what we observe here, we could in principle say that any coordinate vector x according to basis, let me call this one basis Bm, where m can be any number. This would be equal to the matrix which is composed of the basis vectors of Bm. This would be inverse Pm, x, Bm. So this is the generalization of how we can go from one basis to another. Now, we should not forget that we use the standard basis as a very strong support, because we know that by multiplying the original basis, if we multiply the projection onto Bn with the matrix of Bn, this far, so this part here, this is the projection of the vector in the standard basis. Okay, this is how we traditionally write things down. So this is the standard basis, this region, this part here. Then we multiply with P inverse to go into the new domain. But please take a note of these indices that we have reported on the board. Now, for what you see on the board, do you have any question? Is there anything which is not not clear? And so this is okay. So this is all the essence of chapter 7. It is a very fundamental. Now, we can give several examples, but they will all include the same similar steps. Now, to make this a little more visible. Okay, but the most important section of the board is, in fact, the center of the board, where we see how we can move from one basis to another. And those lines in blue, they can just help us how to track down what we are given. I think the examples regarding this three-dimensional space, they are enough. Change of basis. Well, I think so. This product that we see over there, it is in fact, let me think for a moment. Yeah, this is the matrix. So you can consider this one. I can erase because I'm looking at some examples which we could go over. So you can look at this problem and just add okay, now everything is clear. Now, if you are in an exam or when you are doing your homework, it's always good to draw this sketch and to figure out, because you don't need to memorize this. This you could memorize probably, because you know that at any basis you multiply with its own matrix without taking the inverse. You are in the standard basis, and from standard basis to wherever you want to go, you use their respective matrices, okay? But their inverses. Okay, but it's good, so let's, I think we have more space on this side. Well, I believe we can even erase this. So we are focused on changing basis from one. So we know what these are, right? PB and PB prime, they will be the respective matrices which correspond to the respective, which is composed of the vectors of the basis. So how can we change from one to the other? Well, we know that if we go from B to B prime, first we need to find what is V in standard basis. This is here, vector B, B. And then we find that B prime is equal to P inverse B prime times B. And we have a theorem, and the theorems, I believe, in fact, what we had on the board before a while, it was really clear, but it's good to see the formulation of the change of the basis also in the formal way. So given that if B and B prime are both bases of Rn, okay, and B is composed of bases V1, V2, Vn, then transition matrix from B to B prime, from P to B prime is matrix M. Matrix M is equal to V1 in B prime, V2 in B prime, Vm in B prime. Okay. So it is also worth to define this in this way, because in the previous what we had before on the board, we had something like this, where we initially had the PP, right, and we had P inverse of B prime. So this is how we were formulating this just before a couple of minutes. Now it looks like when we multiply these two together, what we are really getting, and let's not forget that what is this matrix, just for a moment, this P inverse B prime, this is multiplying with PP. What is PP in itself? It has these, V1, V2, Vn. So it looks like this is something that we probably did not know, or it was not so clear to us, that if whenever we're multiplying these, this is effectively writing down all of these columns here as projections of these vectors onto this new domain. Okay, so this is what this means. This V1, which we clearly see here, it will be projected onto V1. So personally, I think to do the correct transformation, this is enough. Okay, so even using intuition and everything, or what we saw a few minutes ago, this is enough. But this provides us a little more deep insight. Okay, so we are happy that some numbers that will come out of here will do the work, but we might not always notice that what these come out to be with respect to what they were. Okay. Now we could see another example. It's always good to do examples. Let's assume we have a basis B, 1, 2, minus 1, 1, and we have another basis S, which is composed of 3, 1, and 5, 2. So they are both bases of R squared, okay? We have no doubt of this one. These are the basis of R squared. So once we look at this, the first thing that we should write down, okay, on a piece of paper, is to notice that we have two matrices P and Q, which are 1, 2, minus 1, 1. And this is the matrix Q, which is equal to 3, 1, 5, 2. Okay. So far, we know nothing. We're just given a couple of bases. We immediately write down the matrices, and then we try to formulate the big picture, which is the following. We have the standard basis. Let's consider this one SB. This is the standard basis. We have the basis B here. We have the basis B, which we move this way with matrix P. And we have the other basis S, which we can move to the standard basis using the matrix Q. Okay, so that's always how we do it. We can have another basis here, which is basis S3, which is going to move to the standard basis using its own basis that we are given. Now, so this is what is given so far, okay? Then, given some new information, which is x according to basis B, this is equal to 4 minus 1 according to basis B. What is xs? Find xs, okay? Which means that we are given here 4 minus 1. And we are asking, how does this vector appear down here? Now, it should be easy for us, because to obtain this, first, what should we first do?
Find the x in standard basis.
That's correct. So let's find the x in the standard basis, which is going to be equal to x in standard basis will be equal to p times this vector, right? So this is equal to 1, 2 minus 1, 1 times 4 minus 1 according to b, and this is going to be equal to 4 plus 1, 5, 8 minus 1, 7. I believe this is correct. This is 5, 7. This is the first step. The second step is that now we should move from the standard basis to the S basis, and the only way to do it, we should go with Q inverse. Okay, we should always keep track of those. And the question is, what is Q inverse? Q inverse, we can write it somewhere here. Q inverse will be equal to, if the matrix is 2 by 2, it is relatively easier to figure out what we are going to get. And this is going to be 2, 3. There is an algorithm for this one. We exchange the places of 2, 3, and then we put minus 1s. This is minus 5, minus 1. Minus 5, minus 1. Personally, I don't always remember this. I can derive it, but I always forget it. So now the question is, we want to find what is x according to the basis S, and this is equal to Q inverse times x, which in principle is Q inverse, and x was equal to P times x in B, right? So because P times x in B, we found x in standard basis, the rest is the same, then we say that x in this S is equal to 2 minus 1 minus 5, 3 times 5, 7, and this would be equal 10 minus 35. What is this? 10 minus 35 minus 25. And then we have minus 5 plus 21. We get, what is this, 16? Yes, minus 25, 16. Okay, so this is the Sx. And the question, another question could be the following. What is the transformation matrix? What is the matrix that did this? The matrix that did this, it was this. Q inverse times P. So the matrix M will be equal to Q inverse times P, where this is 2 minus 1 minus 5, 3 times P, which is in this case 1, 2 minus 1, 1. If we multiply those, what we get is minus 8 minus 7, 5 and 4. Okay. Any question? Now, we can have a look a little in detail with what this theorem is saying. Okay, so allow me to remove this for a moment. And let's try to see how we obtain this, this M. In fact, it is, now that I have it in 2 by 2 matrix, it is relatively easier. Because the question is, how did we get these? Okay? How do we get these? We look at the basis of, so what is the basis of P? Wait a second, this is, so we were transferring transition matrix from B to B prime. Okay, we are going from B to B prime, and here we were going from B to S. Okay, this is what we did. So we went from B to S. We follow the same path. What were the unit vectors of B? Sorry, the basis vectors, V1, V2. So if we have a look here, what are the unit vectors in this theorem? Allow me to write here, instead of V1, V2, V3, let's assume there are many like these, but one of them is 1, 2, right? So I know there is in the whole theorem. The other one is minus 1, 1, minus 1, 1. Okay, let's keep this here. Then our question here is, we want to find these. And how do we find these? It's good that we kept this theorem here. We have not removed it yet. We need to find how 1, 2 looks around, but now it's not B prime, it is S, because the other basis, according to the example that we just solved, this was keeping the theorem so that we don't lose the information. If we erase it, we might forget what it looked like. So this is going to be S, and then we want to see how this minus 1, 1 looks in the projection onto S. Okay. How can we find it? So given vectors that look like this, how can we see how they look them according to S? We need to multiply them with Q inverse, right? So that's all we need to figure out. So we say that V1, according to basis S, this will be equal to the, let's do this again, what was it? 1, 2, according to S. And this is always equal to the Q inverse. So let me also say something. I want to pick someone from the class. So here, let me find one randomly. We have here Marvi Giovanni.
Yes.
Marvi, I don't know if you want to. When we say that the column of the basis B it is 1, 2. What is this according to what? Is it according to the standard basis? Is it according to the basis B or basis S?
B. B.
Për nëma e parë, kur themi që normalisht po flasim për baza të ndryshme, po kur themi për bazën B, që përbëhet në matrica P, kur themi kjo 1/2, si e themi këtë? E themi duke u bazuar te baza standarde apo te një bazë tjetër?
Standard.
Eksakt. Të ke shumë të drejtë. Pra ne vërtet kjo B-ja është një bazë që nuk është standarde, edhe pse është standarde. Po ama, kur shohim 1/2, minus 1/1, 3/1, 5/2, këto janë të gjitha në bazë standarde. Pra ne zbulojmë nga to dhe ne dim fare mirë që çdo vektorë që i kemi këtu, që janë në bazë standarde, ne dim si t'i çojmë atan, e dim si t'i çojmë në baza të reja. Pra vetëm gjë që do bëjmë, ky 1/2 fare letër mund ta shkruajmë të direkt. 1/2 është këtu. Tjetër. Minus 1/1 është këtu. Pra, ne i quajmë kështu sepse kështu i lexojmë tradicionalisht, kështu na është mësuar syri. Themi që vlera x është 1, vlera y është 2, which means that the projection of this on the x-axis is 1, the projection on the y-axis is 2. The situation is a little different when we look at this. We say that the projection of this vector is 4 projected on the first column here, okay? And this is the projection is -1 projected onto this column here, okay? But when we talk about these themselves, they are according to the standard basis. Why do we say this? Because if we are here and we want to express them according to S, what we do is that we simply multiply with Q inverse. What is Q inverse? It is on the board, it's something like 2, 3 minus 1 minus 5. 2, 3 minus 1 minus 5, which is 1, 2. Similarly, V2, according to basis S, this is equal to, what was the other one? 1 minus 1, 1, according to S, which means that this is 2, 3 minus 1 minus 5. So what should we get here? Most probably, we should get the columns of M. But if we check it, we get 2 minus 10 minus 8, that is correct. And then we have minus 1 plus 6 is equal to 5. Now, what we did right now on the board, it is really important, so you should keep in mind, because we are going to go to higher degree courses, it is very important for you to always think that when we're changing from one basis to another, you are in principle projecting these into the other domain. Okay? Even me myself, I was. You can spend a couple of minutes looking at these definitions because they are very essential. So similarly, this means the following. This means that the transition matrix from Q to P, it is going to be, wait a second, so we're going from P to Q, and we're taking the transition matrix, it is going to be the projection of this onto this, okay? But if you do the opposite, yeah, okay, that's good. Now, do you have any other question? The next topic is, we have a couple of now, chapter 7, more or less it's over, or at least the major material. What is left is that we can just cover a couple of examples. But if you have no more questions regarding this material, we can also stop this second session.